Okay, so our next talk is by Elijah Bodish on generators and relations for rep Sp2n. Thank you, Elijah.
Okay. I just got a warning that it says my internet connection is unstable. Can you hear me, Carrie?
Yes, we can hear.
Okay. Okay. Yeah, please interrupt me if I'm cutting out, and I can try to do something about that. But yeah, thanks for inviting me, and thanks for organizing such a nice session. All the talks have been great. This is talk about mostly joint work with Ben Elias, David Rose, and Logan Tatham. And I'll just start with some motivation and history about this problem. So we're going to let G be a simple Lie algebra just over the complex numbers for now. And I want to ask the question of how do I get a action of a monoidal category on some category. So I have this monoidal category of finite dimensional representations of this Lie algebra, and I'm looking at some recipe to describe an action of that on just some C linear category. C doesn't have to be a monoidal category. In other words, what I'm trying to do is find a way to construct monoidal functors out of this category of representations to the category of endofunctors of this C linear category. So the first step in this process is that we want to replace the whole category of representations of this Lie algebra with some more combinatorial subcategory that we can study in its place. So I'm going to let fund G be the smallest monoidal subcategory, which is just the full subcategory monoidally generated by these objects L of omega or L of pi for pi a fundamental weight. So you remember that these are the fundamental weights are in bijection with the simple roots of this Lie algebra. And it's familiar probably to many of you that you can recover all of the representations of this group by taking just all sums and direct summands of just the fundamental representations. So we've had a little bit of a discussion of this circle bimodule. So you should think of this fund G, if you're more familiar with the story there, as being something like the Bott-Samuelson bimodules, and rep G is something like the actual Hecke category. And so because this Karoubi envelope has some nice universal property itself, in order to get an action of rep G on a category, we can just get an action of fund G on a category. Fund G is a monoidal category, so we're looking for monoidal functors out of fund G. And this problem, which Cooperberg posed in his paper, rank 2 spiders for rank 2 Lie algebras, was to find a generators and relations description of this category fund G as a monoidal category. In other words, just as I've been pointing out, this is just to describe a universal mapping property for monoidal functors out of fund G, or some universal property to get fund G to act on a category. So a familiar example of this is that if I wanted to get rep SL2, this monoidal category, to act on some category, well, first just note that fundamental representations of SL2, there's actually only one. It's just the vector representation. So I'm going to take this category, which is monoidally generated by the vector representation. So I allow all arbitrary tensor products of the vector representation with itself, and then any SL2 intertwiner between those tensor products. And in order to get a functor, a monoidal functor out of fund SL2, what I need, into the endofunctors of C, I need a single endofunctor of C. And that's basically because there's a single fundamental representation. And then I need some natural transformations between some of the basic endofunctors, like that I have in this setup. So I have F, so I can compose it with itself. I've got the identity, and I need a natural transformation forwards and backwards between these two endofunctors. And I'm also going to insist that those natural transformations satisfy some relations. So I want the composite of these in this order just to be -2, some scalar multiplied by the identity, and some other compatibility conditions, which start to get out of hand when I'm writing them in this sort of classical form of writing the horizontal and vertical composites of natural transformation. So we can reinterpret this in the graphical calculus, and instead of writing the identity of this endofunctor F, I can draw a line, and I can draw this and this for the left-hand side and right-hand side, or left-hand side of both of these equations. So I have some graphical calculus reinterpretation of this problem, and that's going to be the framework that we're working in today. So once I specify this endofunctor and these natural transformations satisfying these relations, that gives me a monoidal functor from this category fund SL2 to endofunctors of C. And I take Karoubi envelope and I get a functor from rep SL2 to endofunctors of C. No problem. So the history of when do we actually understand how to describe this universal property goes back to the 30s in this work of Rimmer, Teller, Weil, and then also independently, basically, in the 70s by Temperley, Lieb, in the case just of SL2. And that's the thing that I just described on the previous slide. And Cooperberg's paper, where he actually posed this problem, here he talks about the case of all of the rank 2 Lie algebras, SL3, SP4 or SO5, and G2. And then later, one of his students came up with a conjectural presentation for the case of SL4 and some other relations that should hold in general for SLN. And then Scott Morrison in his thesis came up with a presentation for SLN, but couldn't prove that it was the right presentation. And then 7 years later, Countess Chemnitzer and Morrison proved that this conjectured presentation from Morrison's thesis was the right presentation. So they described a universal property for the category of fund SLN in terms of monoidal functors mapping out of it. And then the thing that I wanted to talk about today is this recent work where with Elias, Rose, and Tatham, we did the same thing, but for the symplectic Lie algebra, or the symplectic group. So generalizing from SP4 to Sp2n. So I guess, yeah, with the bit of history, this sort of is the end. Like there's other Lie algebras, and so there's still open problems in this area. And let me just mention a few of the applications of having this universal property. So going quite a ways back, Eddinghoff and Ostricht used this universal property to classify semi-simple module categories over rep of G, but just for the case of SL2. There's this work that Ben was talking about on Friday, the quantum K-theoretic geometric Satake. And both his approach as well as the Countess Chemnitzer approach, which are different, and his work with Elias and Williamson, sort of rely on this generators and relations description of representations of Lie algebras. And this has been employed by Ben and Jordy for I guess the SP4 and the SL2 and SL3 cases, and then Countess Chemnitzer have their own version for SLN. But basically, because of the limited technology of different types of Lie algebras here, that's somewhat the end of the story at the moment. As Melissa was just talking about, not homology and categorification, I mean, this is where Kovanov got the idea for Kovanov homology, more or less, is that you have some description of the category of representations for SL2 or for SL3, and he was able to describe SL2 and SL3 homology. And then that approach using sort of generators and relations for foams is generalized to SLN by Queflik and Rose. Also some applications to modular representation theory, Borel, Libiditsky, Sentinelli, and then Tubenhauer and Wedrick were studying representation theory of SL2 from this perspective. And also recent work of Brunden and Tova, Eisenbud, Eddinghoff, and Ostrich studying the semi-simplification of the category of tilting modules for SLN. So the one thing I just wanted to point out, which maybe isn't so important for what I'm going to talk about, but it's good to have in mind, is even though I framed this as we want some universal property for rep G, it's quite important in these applications that whatever our presentation of rep G is, we want it to be able to deform to representations of the quantum group, as well as have some integral form, which then we can relate to representations of this, something like the divided powers quantum group. So we have some good control over the modular representation theory. We can specialize to roots of unity or to positive characteristic, and our presentation still makes sense there. So that's basically the background and motivation that I wanted to say. Now on to sort of what we've been thinking about. So you have this 2n dimensional vector space. We're focusing now just on the symplectic group, and it has an action of the symplectic Lie algebra for V, which is preserving some non-degenerate skew-symmetric 2 form on the vector space. And this Lie algebra has some Lie theoretic data associated with it. It has a Dinkin diagram of type Cn here. And the fundamental representations are in correspondence with the fundamental weights, which are in correspondence with the simple roots, which are again in correspondence with the nodes of this Dinkin diagram. So for type Cn, or for SPV when dim V is 2n, there should be n fundamental representations. Just like for SL2, there is only one fundamental representation. SLN, there's n fundamental representations. Sp2n is also n fundamental representations. SLN, there's n minus 1 fundamental representations, is what I meant to say. And some of them have, I guess they actually all have sort of reasonable linear algebraic descriptions. So the first fundamental representation is just the vector representation. This is an irreducible representation for the symplectic Lie algebra. The second fundamental representation is a quotient of the exterior square of the vector representation. And the reason you have to take a quotient for the symplectic group is that it's preserving this non-degenerate 2 form, which is actually spanning some line inside of the exterior square. And in more general settings, like you have each of these fundamental representations is realized as some subquotient of wedge I of V, and it's the quotient of wedge I of V by the image of, well, I take some I minus 2, there's something in wedge of I minus 2 of V, and then I wedge that with this non-degenerate 2 form that spans some sub-representation, and I can take the quotient. So those are our fundamental representations, and we're trying to understand rep SPV from a generators and relations perspective. And as I motivated at the beginning, or tried to suggest we want to do in the beginning following Cooperberg, instead we're just going to study fund, this category of fundamental representations for the symplectic group. And again, we kind of want to replace the symplectic group with the quantum group so that we have this nice general description of our category. And our theorem is this is equivalent to the CQ linear monoidal category given by generators and relations, where our generators are Well, the objects are going to be some formal object that we think of as corresponding to one of the fundamental representations. So here's V, L of the second fundamental, L of the nth fundamental. And then there's some maps, which like in the case of the temporally Lieb category are like these cups and caps, but now because we have more fundamental representations, there's some more complicated maps between them. So we have cups and caps, but we also have some trivalent morphisms that go from say 1 tensor K to K plus 1. So this map, for example, corresponds to something that's like V, a map from V tensor L of omega K to L of, and then you go to the K plus first fundamental representation. These morphisms satisfy some relations, and I'm just going to put them here. I'm not going to fixate on it too much. The important thing to note is I've got quantum integers in my relations, and this is my convention or our convention for the quantum integers, that it's these rational functions that are quantum n is q to the n minus q to the minus n over q minus q inverse. And I can define quantum factorials and quantum binomial coefficients in the natural way once I know what a quantum integer is. So my relations are something like, go ahead.
Can I ask a question?
Yes, please.
So your trivalent vertices, do they satisfy, like if you bend one of the rungs upwards, does it become the other?
Yeah.
Do you have
Yeah.
like real isotopian variance? It's not.
I'm just like ignoring that in this statement.
I mean, I assume so, but
This is presented as, yeah, with full isotopy.
Okay. Cool. And these are unoriented diagrams.
These are unoriented diagrams. This one nice thing is that having this two form around, I mean, all of these fundamental representations are self-dual for the symplectic group.
Cool.
Yeah, and they're sort of coherently self-dual, so we can get rid of the orientations completely. So these relations are of the form of, that are sort of similar to what we saw before. There's some isotopy that we're ignoring or building into the statement somehow. And then we have a relation that I can get rid of a circle at the cost of a scalar. I have associativity of these trivalent morphisms. If I have some map between two of these generators which are different, so if K and K plus 2, this is a map from an irreducible to a non-isomorphic irreducible, so that has to be 0. This map is an endomorphism of some irreducible representation, the kth fundamental, so it has to be a scalar multiple times the kth fundamental, and ends up being this one. And then there's an exchange relation here where if I take this diagram, which is like an H-shaped diagram, I can rewrite it as a linear combination of other diagrams. And one thing to keep in mind with this right-hand side is that this is sort of re-expressing this diagram as a sequence of something like projection and inclusion, and then some other simpler thing, and then projection and inclusion.
So can I ask, it's simpler in the sense that the labels for the indices are decrease.
Yeah.
Like there's K plus 1 on the left and the
and K minus.
Okay.
And K minus 1. Yeah. So you're able to decrease the label. Yes. So this is the presentation, and how do we want to sort of, like, I mean, what sort of do I have to say about this? I mean, the first thing that I want to suggest is that, well, in order to understand this presentation, as I'll point out, it was important to, for our work, introduce this new diagram. So there's going to be this other diagram X, which isn't in our presentation, but one of the relations that we had that I was sort of saying was you could take this diagram and write it as a linear combination of 3 things, one of which lowered the label. In the case when you go from, I guess, if k plus 1 is 2, k minus 1 is 0. So in this special case where you have a 2 labeled rung here, you get the identity. And it gives you a relation where I have something on the left-hand side and something on the right-hand side, and I can rotate the left-hand side by using these cups and caps, and then I get whatever I have on the right-hand side. So in this endomorphisms of V tensor V, I have some new map, which isn't like an actual generating diagram. It's a linear combination of some of my generating diagrams, and it has this 90-degree rotation invariance property. And I mean, I'm going to say more about it, but sort of one nice thing about this diagram is that it takes the expression for the braiding of V tensor V from this maybe slightly more complicated expression that has some denominators in it, and gives you this slightly more, to me, pleasant expression for the braiding. But this diagram really is the main idea of our proof that this result that we have a presentation for fundamental representations for the quantum group associated to the symplectic Lie algebra. And the first thing that we want to do, which actually doesn't use this crossing, but uses something about the braiding, is that you just need to show that the relations hold. So let's just suppose that that's fine. And after that, the important thing to do is to relate this presentation to some other category that we understand better. And that's going to be, instead of thinking about fundamental representations, we're going to think about this category just generated by the vector representation. But we allow arbitrary tensor products of it, and we take all Sp2n intertwiners between tensor products of these representations. And this has been very well studied in the literature as sort of under the guise of the BMW algebra. But we take a slightly different approach where we allow, instead of generators given by the crossing, we're going to use our generating morphisms, our cups and caps, and then this new diagram X. And then we only have a single object instead of these n distinct objects. And we have this new set of relations, which is some reinterpretation of the other relations, but in terms of just this crossing diagram and instead of these other trivalent diagrams. So what are our relations here? Well, I have now only one circle that I can evaluate. I get a scalar. I have an endomorphism of V where I twist using this X map, and I get a scalar multiple of the identity. I have this relation, which is like a Reidemeister 2 relation. I have this relation, which is sort of a deformed Reidemeister 3 relation, since I have all of this error term here. And then the last relation, which is really the part that depends on n, is that if I take the half twist on n strands, but not in terms of the braiding, in terms of this crossing map that's 90-degree rotation invariant, I can rewrite it as a linear combination of diagrams where no sub-diagram in my picture, once I write it in terms of these x's or cups and caps, has a half twist in it. So I can sort of get rid of these permutations that have this pattern that's corresponding to the half twist on n strands, as well as getting rid of the pattern for more than that. So I can get rid of all of the half twists for n greater than or equal to n. And this relation, we don't know exactly what the form of it is, but we know that we can do it. And that ends up being enough to give us the result. So basically using this relationship, as well as some knowledge about this relation that we can take the half twist and rewrite it, we can count the dimensions of invariant spaces in this category. And some work of Sundaram allows us to relate that to our diagrammatic calculus, and the result follows from that. So I just want to say the idea for this X map in end of V tensor V, remember in Cooperberg Spider's paper, he studied SP4, and we're working in Sp2n. And actually, this idea for this specific map already appeared there. So it's a natural thing to write down, because when you have this topological description of your category, allowing isotopy and cups and caps, you are looking then for some endomorphism which has this 90-degree rotation invariance property, and this map kind of comes to you from that. And as I said out loud, but it's really important to say again, I mean, the idea that somehow the combinatorics of taking diagrams built out of a crossing and getting rid of all of the half twists on end strands are related to the dimensions of invariant spaces. This appeared in Sundaram's thesis. And this is the key sort of result that we're using at the end of the day. The other thing is that there's in the BMW algebra, there's an idea from this paper of Fischl and Gronowski about a canonical basis, kind of an analog of the canonical basis for the Hecke algebra, but instead of in type A and types B or type C or D. And in the case of the ring end of V tensor V over Sp2n, this crossing map is one of the canonical basis elements. So this crossing map is somehow like appearing in other settings as well. So it comes naturally, not just from the topological perspective, but also from this perspective that they had where they're thinking about a canonical basis for BMW algebras. And then the other thing I want to say is that it's maybe work in progress or open, or it's not really clear to me. Maybe it's even already understood, but just in some other language, to actually understand explicitly how to rewrite the left-hand side in terms of these crossings and cups and caps diagrams. What exactly is this relation on the right-hand side? And we're sort of conjecturing, I think it's pretty reasonable, that the coefficients are lying in this base ring Z adjoint QQ inverse, which seems to be related to a conjecture from several years ago by Hu and Zhao, when they were thinking also about BMW algebra. So if you related this diagram to what they were thinking about in terms of BMW algebra, there should be some way of understanding the coefficients, maybe in terms of some quantum Pfaffian, since the Q equals 1 version of this relation is known to be related to the classical Pfaffian. So more or less, there's this new web category that describes fundamental representations for Sp2n. In order to prove that our set of relations is a complete set of relations, we had to go through and study this other category built out of crossings. And this category built out of crossings is kind of interesting in its own right. It's similar to the BMW category, hadn't been studied before, except for in the case of Sp4, I guess, in Cooperberg's paper. And it has this relationship to the canonical basis from the Brouwer algebra. Did I hear somebody going to say something?
Sorry, that was me. I forgot to mute my microphone.
No, it's okay. Yeah.
I was going to ask if the other coefficients were obviously polynomials, but I think I answered my own question.
Right. Yeah. So there appears to be poles, but then they kind of cancel out with zeros. So these are all the coefficients here are in Z adjoint QQ inverse. And then in our web category, for Sp2n, there's irremovable poles in our relations for quantum numbers that are less than n, or I guess less than or equal to n. So you need to invert quantum 1, quantum 2, quantum 3 up to quantum n in order to define this fund category for Sp2n. which is again different than what we're used to for SLN. Okay.
Sorry.
That-
just-
yeah,
do
yeah,
I understand? I'm sorry, just about the last thing you said. Do I understand that like basically the projectors that project onto the fundamentals have these denominators? Is that what you mean?
yeah.
Yeah, I suppose that would in this algebra that would project onto those guys have these denominators of like quantum whatever.
Exactly. Yes. The fundamental representations don't have Z adjoint Q inverse. They don't have Z adjoint Q inverse forms that are self-dual, I guess is.
Oh, I see. Weird. Okay.
They have Z adjoint Q inverse forms as file modules, but they're not tilting modules. So this is like actually great. This is what I was just about to point or start to talk about. So what else is there to think about just on the basics of like understanding this category as a category and not trying to follow through with whatever I was pointing out as potential applications or applications of previously understood web categories early in the beginning of the talk. So this is exactly what Matt was asking about. If you just in general, I'm going to say let this set of quantum k's be the set of denominators contributing poles in relations in whatever your category is, your web category. And so the case of SLN, this is just the empty set. SLN, this all of the fundamental modules here have Z adjoint QQ inverse forms, which are self-dual and irreducible. And the SP4 case, you need to invert 2. And for Sp2n, you need to invert 2, 3, 4, all the way up to n. So this is like our base ring now, is we're going to take Z adjoint QQ inverse and then invert everything that we need to invert. So that means that our diagrammatic category has an integral form defined over this ring. So if we base change to C adjoint Q, we know that we're going to have an equivalence to fundamental representations of our quantum group, but we kind of want to think about how do we understand this category as in its integral form, and then maybe base changes to other more interesting fields like specializations where Q is a root of unity, or Q equals 1, and you're at a impositive characteristic. And so the thing that we do know is true in general is I can take the quantum group, and this is going to definitely be defined over this ring A, and I can base change that to a field, any field that I want, and consider fundamental representations for this guy and take its Karoubi envelope. And this is what people call the category of tilting modules. So this is a monoidal additive category, which is not abelian in general, but it's got a bunch of self-dual objects in it, which have nice, well understood, somewhat understood characters that you can compute using your diagrammatic calculus. And the hope is to relate this category of tilting modules with the sort of integral diagrammatic category here. But it's not at all obvious that there is necessarily a relationship between this integral diagrammatic category and the category of tilting modules, even though you want there to be one. So the question is, when are these two things equivalent? And the answer, sort of the partial answer, is known in some cases. So my understanding is that the first time that somebody proved this is Ben Elias showed that there's a equivalence between this integral fundamental category for the divided powers quantum group for SLN and the Countess Chemnitzer Morrison Webb category, but just you work over Z adjoint Q inverse instead of over C adjoint Q. And then using similar ideas, I was able to show that this is true for SP4. This is something before the Sp2n Webb category had been written down, and I guess, sort of just, it was done in parallel to some work in progress for the other rank 2 case from Cooperberg's paper for G2. That's something that Victor Ostrick and Noah Snyder are thinking about. And then our expectations is that this will probably, the same sort of thing will work for this integral version of our diagrammatic category for DSP2N, but we are still sort of several steps away from that. In particular, we don't actually even know where these trivalent maps go in terms of representation theory. We just know that there is a functor. We don't really know how to construct it explicitly. And the ideas here really used an explicit description of this functor. So I'm out of time, but let me just say there's one other question that I want to say just something short about. So Morrison in his thesis was saying we could try to study generators and relations for not just the category of tilting modules or the category of representations, but this semi-simple quotient of the category of tilting modules, which is like a very fusion categories, modular categories thing. This is some semi-simple category in the case in general, and in the case that I have here, where you're at a root of unity where the sort of valuation or whatever of the root of the unity is bigger than the Coxeter number, then this problem of finding generators and relations for this semi-simple quotient of the category of tilting modules is just the same as finding explicit formulas for idempotents in the category. And this is something that also Ben Elias thought about for SLN and has proven his answer will work. I mean, he's found all the idempotents sort of in this category for n less than or equal to 4. I was able to do this for SP4, and then with Haihan Wu, we are writing up now the answer for G2. And Ben has a conjecture in general, which he's calling the clasp conjecture, that there's some form of the idempotence that's given recursively like this, where the coefficients are in a special case given by this Lie theoretic data. And I mean, very little is known except for in these very small cases, and it'd be interesting if other people were thinking about this. So I just wanted to advertise it. Okay, thank you. Any questions?
Thanks, Elijah. Does anybody have any questions? Well, first of all, let's thank Elijah for a great talk. And if you have any questions, please open up your mic.
While everyone's thinking of a really basic question, when you're trying to prove these relations or all the relations, in the day-to-day, how are you working with, like, how do you identify the components of like a bunch of tensors of this vector representation? Like, do you work with some like characters, or do you actually look at some matrices? Like, I have no idea what your day-to-day looks like.
Yeah, I mean, like the silliest, but maybe somehow one of the more useful things is like, if you don't have to prove anything, but you just want to have some guesses, you can use the Lie software to tensor product representations together and see how they, for Lie algebras, and see how they decompose. And that allows you to you can do that for small cases, and then you can guess from there. That's something that Logan Tatham taught me, that is actually, there's some pretty easy to access software online. I think if you just type it into Google, you can find it. Yeah, you can just start seeing how these things decompose. And
so the software probably just actually multiplies like matrices out and then like puts them into block diagonal or something.
What the software does, so the software just takes, V tensor W, where these are two, well, what it would compute for you is that if you had two irreducible representations of your Lie algebra, and you want to decompose this into a direct sum of irreducibles, the software can do that, and it uses this thing that's called climax formula, which is it computes some alternating sum of characters using the vowel character formula.
Cool, thanks.
Yeah.
Never heard about this.
Thanks for the question.
So I have another question, and that's whether you have any intuitions for any other types of Lie algebras or maybe super Lie algebras?
Yeah, I haven't thought about super Lie algebras, but it seems to be a good thing. And I guess Kovanov, in a talk that I went to in the past 6 months, even said that he felt like OSP 2.1 or 1.2, maybe, I guess OSP 1.2, right? Even this case wasn't satisfactorily, like he didn't understand that completely, or didn't feel like anybody had studied that case well enough. And that seems pretty approachable. For the classical Lie algebras, I have with the BERT team with Elias Rosentatham, we have sort of conjectures for up to rank 3 for everything. But then after that, I guess it gets a little bit crazy, and maybe one's fantasy is to try to understand how things go for F4, but I have no idea. It seems like you would need maybe a computer or something to make a guess. And I don't yet see, and I haven't talked to anybody who sees that there's like a general framework of like an actual Sayre presentation for these categories that just takes the root system and gives you the monoidal category. It seems to be kind of case by case right now.
Thanks.
Are the expected dimensions of the like endomorphism algebras known at least?
Yeah, probably at least in yes, I guess it depends. Like, I think you can compute the expected dimensions using crystals or the or this like path model thing. And then in the classical case, there's like well-known like Tableau theoretic combinatorics that compute these dimensions. And other combinatorial models for things that compute the dimensions. But I guess the tricky thing is, like, once you write down your diagrammatic calculus, the point is to somehow find the combinatorics within that calculus, which is what we were able to do based off of this thing that Sundaram did in her thesis in type C. And I think it's much more complicated in type B. And that's because of the spin representations, which you can't study from the perspective of the BMW algebra. You need more than the BMW algebra to study the invariant spaces of spin representations in type B. Okay, thanks, Ben. Yes.
Okay, so if there's no more questions for Elijah, let's thank him again.